The space is full of galaxies and planets, each with fascinating and slightly terrifying mysteries. Beyond the warm light of our sun, the universe hides places so extreme they seem more nightmares than reality. Imagine worlds where the rain is made of glass shards, darkness covers the sky endlessly, or the surface bubbles with lava. These are not the calm, peaceful planets we have dreamed of. They're the most terrifying planets in the universe, where the environment is so hostile that life, as we know it, could not survive. This journey will take us to the limit of what we understand about the universe, and each planet that we explore will show us how strange and terrifying it can be. Music BHD 189733b, a planet located 645 light-years from the Earth in the constellation of Volpe, that offers a glimpse of an environment so extreme that it transcends the wildest imagination here in our home planet. This distant world, classified as a hot Jupiter due to its size and proximity to its star, is subjected to atmospheric conditions different from those that are experienced in Estados Unidos or in any other place of the Earth. What especially distinguishes HD 189733b is its famous crystal rain, a phenomenon that, although it may seem like science fiction, is a scientifically documented reality based on the atmospheric composition and unique dynamics of the planet. The atmosphere of HD 189733b is a scorching and turbulent whirlwind with temperatures exceeding 1,000 degrees Celsius (1832 degrees Fahrenheit). This intense heat is a direct consequence of the planet's close orbit around its host star, which exposes it to intense stellar radiation. In this infernal environment, silicate particles can form and exist within the atmosphere. The high temperatures ensure that these silicate particles are not solid, but exist in a molten state, floating in the atmosphere. The wind speeds in HD 189733b present an astonishing contrast with what we are accustomed to on Earth, painting a picture of a world where the air itself embodies forces beyond our wildest comprehension. The most powerful hurricanes, like those that the previous generation experienced in the United States, can unleash winds that reach speeds of up to 250 kilometers per hour, approximately 155 miles per hour. These storms, although formidable and capable of causing significant destruction, pale in comparison to the atmospheric tempests unleashed on HD 189733b. In this distant exoplanet, the winds howled at speeds that exceeded 7,000 kilometers per hour, or around 4,350 miles per hour, a figure that is almost 20 times faster than the most powerful hurricanes of the Earth. Imagine the air moving at such speed that it could cross the continental United States from coast to coast in under 2 hours. This comparison highlights the magnitude of the wind speeds of HD 189733b and the extreme conditions that define its atmosphere. The cause of these extraordinary wind speeds lies in the planet's proximity to its star, which gives rise to dramatic temperature differences throughout its atmosphere. This disparity of temperatures drives the fierce winds, as the hot air rushes toward the colder regions with such speed and force that it defies terrestrial analogs. The concept of wind in HD 189733b extends beyond the mere atmospheric movement and represents a fundamental aspect of the identity of the planet that gives form to everything, from its climatic patterns to the surreal phenomenon of the rain of glass. The presence of glass rain in HD 189733b, a phenomenon as intriguing as it is violent, has profound implications for the planet's surface and the environment in general. Unlike the soft rains that nourish the Earth and give life to its numerous ecosystems, the rain of crystal on HD 189733b is a manifestation of the planet's extreme and hostile conditions. The fragments of crystal, formed from particles of molten silicate trapped in the planet's fierce winds and cooled until solidified, do not simply fall to the surface, but bombard it at speeds of up to 7,000 kilometers per hour, similar to those of the winds themselves. This relentless rain of glass particles shapes the landscape of HD 189733b 733b in ways that are difficult for us to understand from our vantage point on Earth. The surface, subjected to the constant abrasion of these particles at great speed, is probably extremely rugged, with features sculpted by the constant attack throughout geological timescales. The accumulation of glass from the sky could give rise to the formation of vast reflective dunes that would create a landscape that shines in a disturbing way under the light of a nearby star of the planet. The impact of the glass rain extends beyond the physical alteration of the planet's surface. The energetic dynamics of such an environment is unique, with the heat of the nearby star of the planet and the kinetic energy of the glass that falls contributing to an atmosphere that is in a state of perpetual change. This extreme meteorological phenomenon probably prevents the existence of water in liquid form, a fundamental prerequisite for life as we know it, and poses significant challenges for the formation of stable habitable zones. Music 32b, another fascinating exoplanet located about 750 light-years from Earth, holds the title of the darkest known planet discovered in the universe. This distant world reflects less than 1% of the solar light that falls on it, making it darker than coal and one of the most intriguing subjects for astronomers and scientists alike. The cause of 32b's extreme darkness is a combination of its unique atmospheric composition and the chemical reactions that occur within it, phenomena that contrast radically with the most familiar climates and celestial bodies within our own solar system. The atmosphere of 32b contains a high concentration of light-absorbing chemical substances, like vaporized sodium and potassium, as well as titanium oxide. However, unlike the planets of our solar system, where titanium oxide could reflect light and contribute to a brighter appearance, the atmospheric conditions of 32b prevent such reflection. Instead, these elements absorb almost all the solar light that reaches the planet, trapping it in the form of heat. This absorption is so efficient that it prevents the planet from reflecting light back into space, which explains its incredibly dark appearance. Another factor contributing to the darkness of 32b is the possible presence of unknown compounds in its atmosphere. Scientists speculate that these compounds could be responsible for the exceptionally high level of light absorption, although the exact nature of these materials remains the object of investigation. The high temperatures on the planet, which can reach up to 1,000 degrees Celsius, approximately 1832 degrees Fahrenheit, also play an important role in maintaining its dark state. This heat further facilitates the chemical reactions that lead to the absorption of light instead of its reflection. A predominant theory suggests that the atmosphere of 32b is rich in molecules like vaporized sodium and potassium, both known for absorbing visible light. These elements in the high-temperature environment of 32b could significantly contribute to its dark appearance by preventing solar light from being reflected back into space. In addition, the hypothesis of the presence of titanium oxide has been raised in many planetary atmospheres. The titanium oxide acts as a reflector of light. However, in the extreme conditions of 32b, it can contribute to the absorption instead of the reflection of light, which increases the general darkness of the planet. General darkness of the planet. Beyond these known substances, the researchers also speculate with the existence of compounds still not identified in the atmosphere of 32b that could increase even more its capacity of absorption of the light. It is believed that these unknown compounds play a crucial role in the darkness of the planet, potentially representing new types of chemical processes that occur under the extreme temperatures and pressures that occur in this type of music. Music exoplanets Kepler-70b, an exoplanet that exists in a realm of extreme heat, challenges our comprehension of the planetary climates with its astonishing range of temperatures located in a close orbit around its host star. Kepler-70b sustains temperatures that greatly exceed anything found on Earth or, indeed, on the majority of known planets. The range of temperatures on this celestial body can reach between 6,700 degrees C, approximately 12,092 degrees F, and 7,300 degrees Celsius, approximately 13,172 degrees Fahrenheit. This range places Kepler-70b among the hottest planets ever discovered, with surface conditions that resemble the outer layer of a star more than the atmosphere of a planet. The extraordinary heat of Kepler-70b is mainly due to its proximity to its host star, Kepler-70, which it orbits at a remarkably close distance. This tight orbit results in extreme levels of stellar radiation that bombard the planet and heat its surface to temperatures that vaporize metals and rocks, creating an environment that is not only inhospitable, but almost inconceivable in its intensity. The concept of day and night on Kepler-70b is irrelevant due to its close orbit, which results in almost uniform temperatures across the surface, near the limit of what solid matter can withstand before becoming plasma. Moving on from the extreme temperatures of Kepler-70b, it is crucial to explore how its proximity to its star profoundly influences the planet's surface, creating an environment that contrasts radically with any terrestrial equivalent. The intense stellar radiation that Kepler-70b receives due to its close orbit around the host star, Kepler-70, directly impacts the physical characteristics of the planet, creating a surface scenario that defies imagination. The heat from its proximity to the star causes the surface of Kepler-70b to reach temperatures at which metals and rocks not only melt, but also vaporize. This results in a landscape in constant change, with surfaces that may be molten or partially vaporized during the planet's orbit. The extreme heat can create pools of liquid metals and silicates, resulting in a bright and reflective surface that could not be more different from the rocky or water-covered surfaces we know on Earth. The gravitational forces acting due to the close orbit contribute to significant tidal stresses on Kepler-70b. These stresses can deform the planet and cause volcanic activity or create unusual geological formations. Such activity would further alter the surface of Kepler-70b, turning it into a dynamic and constantly changing world where the ground under your feet, if one could stand on it, is as transient as the atmosphere that surrounds it. The extreme conditions that occur on Kepler-70b are a testament to the diverse environments that planets can withstand. This diversity, in turn, offers a unique perspective on the processes that lead to the formation and survival of planets in the universe. The formation of planets, a process that has intrigued scientists for centuries, is influenced by a multitude of factors, including the composition of the protoplanetary disk, the distance from the host star, and the star's characteristics. The existence of Kepler-70b in such an inhospitable zone near its star challenges existing models of planetary formation, suggesting that planets can form and remain stable even in environments that would seem too extreme for such processes. The survival of Kepler-70b in these conditions could indicate that planetary formation mechanisms are more versatile and robust than previously thought, capable of creating stable celestial bodies even under severe thermal and gravitational stresses. The study of the extreme conditions of Kepler-70b can shed light on the final stages of planetary systems. As stars evolve and expand towards their red giant phase, they can engulf the innermost planets, subjecting them to conditions similar to those experienced by Kepler. Music 70b, the planet GJ1, 1214b, an exoplanet located approximately 40 light-years from Earth, reveals a phenomenon that challenges our everyday understanding of water. Known as a super-Earth due to its size and mass, greater than those of Earth, but smaller than those of the gas giants in our solar system. GJ1214b harbors conditions that give rise to what is colloquially known as burning ice. This term, although seemingly contradictory, describes a state of water that exists under the extreme conditions of pressure and temperature that occur on the planet, a state that challenges the solid, liquid, and gaseous phases known on Earth. The concept of burning ice on GJ1, 1214b comes from the planet's dense atmosphere and the depths of its possible oceans. Under the immense pressure exerted by the planet's atmosphere, the water takes on a form known as supercritical fluid, a phase that blurs the lines between liquid and gas. In this state, water retains some properties of a liquid, such as the ability to dissolve materials, while acquiring characteristics typical of a gas, such as filling a container with its shape. This supercritical water is not ice in the conventional sense, nor is it burning in terms of being a flame, but the extreme conditions in which it exists lead to it being described as burning ice. The temperatures on GJ 1214b also contribute to this phenomenon, although they are not as scorching as on some exoplanets. The temperature is high enough to prevent water from existing in a familiar liquid state on the surface, assuming that it exists instead this exotic supercritical phase. This condition creates an environment in which water behaves in a way unlike anything we know on Earth, with the ability to both dissolve materials like a liquid and penetrate spaces like a gas. The pressure on GJ 1214b presents a stark contrast to the pressures found in Earth's deepest oceans, pushing our understanding of extreme environments to the limit. Earth's oceans, deep and mysterious in their own right, reach their greatest depths in the Mariana Trench, where the pressure reaches about 1086 bar, or about 15,750 psi, which is equivalent to experiencing the weight of an elephant standing on a postage stamp, a comparison that vividly illustrates the intense pressure at such depths. However, when we turn our gaze to GJ1 1214b, the concept of pressure enters a new realm of intensity. The atmospheric pressure on GJ 1214b is estimated to be thousands of times greater than the pressure at the deepest point in Earth's oceans. This immense pressure is due to the planet's large mass and density, combined with a thick atmosphere likely composed of heavy molecules. Under such conditions, water and other substances undergo dramatic transformations, entering exotic phases such as the supercritical fluid state mentioned above, where the traditional distinctions between gases and liquids no longer apply. The study of GJ1 1214b, with its intriguing characteristics and distant location, presents a unique set of challenges for scientists. These challenges stem both from the technological limitations of current observational tools and from the inherent difficulties in interpreting data from such a remote exoplanet. One of the main obstacles in studying GJ 1214b, or any exoplanet of similar distance and composition, is the enormous distance that separates us from these celestial bodies located about 40 light-years from Earth. Studying GJ 1214b requires advanced telescopes equipped with highly sensitive instruments to detect and analyze its atmospheric composition, temperature, and other vital characteristics. Another is the resolution and sensitivity of current astronomical instruments. While technological advances have dramatically improved our ability to observe distant planets, there are still limitations in detecting the most subtle details of an exoplanet's atmosphere, especially when it comes to identifying specific molecules or understanding the dynamics of atmospheric conditions. This is compounded by the fact that the signals from these planets are often obscured or diluted by the overwhelming brightness of their host stars, making it difficult to isolate the specific characteristics of the planet from the light it reflects or emits. The interpretation of data from GJ 1214b is complicated by our limited understanding of how certain conditions, such as supercritical fluids, behave under the extreme pressures and temperatures found on such planets. Scientists rely on theoretical models and laboratory experiments to simulate these conditions, but these models have their limitations and cannot perfectly reproduce the complex environments of distant exoplanets. As a result, an ongoing effort is being made to refine these models and develop new techniques to better understand the data we receive from observations of GJ 1214b. Music 12b, an exoplanet located approximately 600 light-years from Earth, has been dubbed the doomed planet, due to its orbit dangerously close to its host star, leading it to a grim fate that has captivated both scientists and the general public. This gas giant, approximately the size of Jupiter, is gradually being consumed by its star, a process that offers a stark illustration of the destructive forces that can shape the life cycle of planets. The main reason why WASP-12b is considered doomed lies in its incredible proximity to its host star, WASP-12. This proximity gives rise to extreme gravitational forces that are exerted on the planet, causing it to be perfectly locked, which means that one side of the planet always faces the star, while the other side remains in perpetual darkness. The side of WASP-12b that faces the star experiences intense heat with temperatures exceeding 2,500 degrees Celsius, about 4,532 degrees Fahrenheit, which causes the planet's atmosphere to be expelled into space. The intense gravitational attraction of the star has caused WASP-12b to adopt an elongated shape, like an egg, instead of the spherical shape typical of planets. This deformation is a clear indicator of the star's powerful influence on the planet. Observations have revealed that WASP-12b is losing mass at a rate of about 189 trillion tons per year, a significant portion of its total mass. This loss is due to the heat and gravitational attraction of the star, which strip the planet of its outer layers, a process known as atmospheric escape. Scientists predict that in a relatively short astronomical period, possibly as little as 10 million years, WASP-12b could be completely devoured by its host star. This final consumption underscores the planet's doomed state and highlights the dynamic and sometimes violent nature of planetary systems. The study of WASP-12b and its inevitable disappearance provides valuable information about the life cycle of planets, especially those in orbits close to their stars, and serves as a reminder of the powerful forces at work within our universe. Observations of WASP-12b's deadly spiral toward its host star provide a fascinating and somewhat sinister view of celestial mechanics in its most extreme form. Astronomers, using powerful telescopes and space observatories, have collected critical data about this doomed planet, allowing us to understand the process by which it is consumed by its star. The most compelling observations come from a detection of a vast cloud of material being dragged from WASP-12b toward its star as a direct consequence of the planet's close orbit and the immense gravitational forces at play. This material forms a kind of extended atmosphere or exosphere that extend from the planet to the star, creating a gas bridge that is slowly being extracted from WASP-12b. Spectroscopic analysis, a technique that allows scientists to determine the composition of celestial objects by analyzing the light they emit or absorb, has been instrumental in studying this phenomenon. Through spectroscopy, astronomers have identified several gases in this stream, including hydrogen, helium, and heavier elements, which are being torn from the planet's atmosphere and added to the star. Other observations have revealed that the rate of mass loss is so significant that the shape of the planet has been distorted, elongated by the tidal forces exerted by the star. This distortion not only affects the gravitational balance of the planet, but also accelerates the process of atmospheric escape, hastening the disappearance of WASP-12b as the planet loses mass to its star. The atmosphere undergoes significant changes, with large amounts of gas being torn away. This loss includes not only hydrogen and helium, the most common elements in gas giants, but also heavier elements and compounds that contribute to the planet's atmospheric composition. The stripping of WASP-12b's atmosphere leads to a decrease in atmospheric pressure, altering the balance between the planet's surface and the vacuum of space. In addition, the intense heat from the nearby star causes the remaining atmosphere to expand and escape more easily, further accelerating atmospheric loss. This process can cause the atmosphere to become thinner and less able to protect the planet's surface from harmful stellar radiation, leading to increased surface temperatures and alteration of the chemical composition of the surface itself. The tidal forces exerted by the star on WASP-12b not only elongate the planet, but can also induce volcanic activity or other geological processes on the surface by heating the planet's interior. This geothermal heating could reshape the planet's surface over time, creating new surface features or eroding existing ones. The study of the death spiral of WASP-12b not only offers a window into the fate that awaits the planet, but also has broader implications for our understanding of planetary evolution and stars and planets. These observations have challenged previous notions about the stability of planetary orbits and the factors that can lead to the destruction of a planet. Music. Moving from the captivating but terrible circumstances of WASP-12b, we delve into the enigmatic case of HD 106N6b, a planet whose peculiar and altered orbit offers a stark contrast to more conventional planetary systems. HD 106906b is an exoplanet located about 300 light-years from Earth and presents a curious case for astronomers due to its highly elliptical and distant orbit around its host star. This exoplanet is located at an astonishing distance of more than 650 times the distance from Earth to the Sun, placing it in a part of its solar system where traditional models of planetary formation and orbital dynamics struggle to offer clear explanations. The altered orbit of HD 106906b raises intriguing questions about the processes that could lead to such an unusual arrangement. A prevailing theory suggests that its current orbit is the result of gravitational interactions with other planets within the system or even with a passing star that could have drastically altered its trajectory. Such an encounter would have to be both powerful and precise to push HD 106906b into its current trajectory without ejecting it from the system entirely or causing it to crash into its host star. Another aspect of the orbit of HD 10696b that fascinates scientists is its inclination. Observations indicate that the planet's orbit is significantly inclined relative to the plane of its solar system, further complicating the mystery of its origin and evolution. This inclination could be evidence of a dynamic and possibly turbulent past within its solar system, with evolutionary interactions that are not yet fully understood. The unusual orbit of HD 106906b not only captivates the curiosity of astronomers, but also poses a significant challenge to our existing theories about the formation of planetary systems. Traditionally, planetary formation models have focused on the concept of a protoplanetary disk, a rotating circumstellar disk of dense gas and dust surrounding a newly formed star, where planets form through the accretion of material from the disk. These models predict that planets should form within the disk and maintain orbits relatively close to the plane in which the disk lies, similar to the configuration of our solar system. However, the extraordinary orbit of HD 106906b, with its significant distance from its host star and its inclined orbital path, suggests that other processes may be at play in the formation and evolution of planetary systems. One of the main challenges posed by the orbit of HD 106906b is understanding how a planet can end up in such a wide and inclined orbit when traditional formation mechanisms do not predict such results. This discrepancy suggests interactions beyond simple accumulation and the dynamics of the disks. Theories have been proposed that include gravitational perturbations from other massive bodies within the planetary system, such as other giant planets, or even close encounters with passing stars that could drastically alter a planet's trajectory. These scenarios imply a more chaotic and dynamic early solar system environment than previously assumed. In addition, the existence of HD 106906b challenges the notion of how such stable planetary orbits are achieved and maintained. The planet's current orbit suggests that it may have gone through a complex migratory history that could involve mechanisms such as planet scattering or capture from another system, which could involve mechanisms such as planet scattering or capture from another system. These processes could give rise to the great variety of exoplanetary systems observed by astronomers far beyond the relatively orderly configuration observed in our solar system. From exploring the challenges that the unusual orbit of HD 106906b poses to traditional theories about the formation of planetary systems, let's delve into the speculative but intriguing possibilities of what might have caused the extraordinary orbital characteristics of this exoplanet. The orbit of HD 106906b, notably different from the more familiar patterns observed in our own solar system, suggests an origin history full of celestial dynamics that expand the limits of our knowledge. A convincing theory suggests that the orbit of HD 106906b results from gravitational interactions with another unseen companion in the system, possibly another planet or brown dwarf. These interactions could have drastically altered the trajectory of HD 106906b in the beginnings of the history of the system, expelling it to a distant and inclined orbit. This scenario would require a delicate balance of forces to ensure that HD 106906b was not completely expelled from the system, but established in its current wide orbit. Another hypothesis suggests that a close encounter with a passing star could disturb the young planetary system, influencing HD 10696b's trajectory. Such an event could occur in the dense environment of a stellar cluster where close stellar encounters are more common. The gravitational pull of a nearby star could significantly alter the speed and direction of HD 106906b, placing it on its unusual course. In addition, the early dynamic evolution of the HD 106906 system may hold clues about the planet's strange orbit. The planetary scattering process, where young forming planets interact and gravitationally launch each other into different orbits, could explain HD 106906b's current position. This mechanism often results in one or more planets moving to wider and more eccentric orbits, which could lead to the highly inclined orbit observed in HD 106906. Music. The intriguing exoplanet Corot 7b, located at a distance of 489 light-years from Earth in the constellation of Monoceros, presents a phenomenon as fascinating as rock rains. Due to its extreme environmental conditions, this planet constitutes an extraordinary case in the study of exoplanetary climatic patterns, mainly due to its proximity to its host star Corot 7b orbits around its star at a distance 23 times closer than the orbit of Mercury around the Sun, which causes temperatures on the surface of the daytime side to reach up to 2,500 degrees Celsius, 4,532 degrees Fahrenheit. At such high temperatures, the rock on the surface of Corot 7b not only melts but also vaporizes, creating an environment in which minerals and rocks become gas, a scenario very different from anything we experience on Earth. The intense heat on the daytime side of the planet causes the rock to vaporize, and this rock vapor is transported by the planet's atmosphere to the colder nighttime side, where temperatures drop significantly, allowing the vaporized rock to condense and form particles that eventually fall as precipitation, not to the rain on Earth, but instead of water, they are literally rains of rocks. This vaporization and precipitation cycle is a constant characteristic of the atmosphere of Corot 7b, driven by the extreme temperature difference between the daytime side and the nighttime side of the planet. In addition, the gravitational forces that act between Corot 7b and its star contribute to the distorted shape of the planet, which affects the way the atmosphere circulates these rock vapors. The tidal forces are so strong that they influence not only the planet's shape, but also its internal heating, adding another layer of complexity to the observed climatic patterns. The unique atmospheric phenomena of Corot 7b, where temperatures can reach 2,500 degrees Celsius on the daytime side, turning rocks into vapor, and then see how these vapors cool and condense into rock rain on the colder nighttime side, offer a living laboratory to study processes that it is simply not possible to observe on Earth or within our solar system. This intense cycle of vaporization and precipitation in Corot 7b provides very valuable information about the behavior of minerals and rocks in conditions that are extreme by terrestrial standards. For example, understanding how different materials vaporize and condense can help scientists refine models of planetary formation and evolution, not only of exoplanets, but also of the early Earth and other bodies in our solar system. This could shed light on our planet's geological history, including the formation of its atmosphere and the development of its crust. In addition, the study of atmospheric dynamics in Corot 7b allows researchers to explore the effects of extreme temperature gradients on atmospheric circulation. These insights could improve our understanding of atmospheric science, including weather patterns and climate in a wide range of planetary environments, from the hottest exoplanets to Earth-like worlds. The extreme conditions of Corot 7b challenge our existing theories about the habitability of planets and the conditions necessary for life. By expanding our knowledge of how planets can form and evolve in a wide variety of conditions, we can better assess the potential for life elsewhere in the universe. This knowledge also helps in the search for exoplanets, as it helps identify which characteristics might indicate that a planet is more habitable or at least interesting to study. Music. Scientists have been captivated by 55 Cancri e, an exoplanet twice as big as Earth and located about 40 light-years away in the constellation of Cancri. Due to its extraordinary characteristics, it is believed to have a surface rich in diamonds. This hypothesis derives from the planet's unique composition and the extreme pressure conditions it harbors. 55 Cancri e is mainly composed of carbon in the form of graphite and diamond. Unlike Earth, which has a rocky surface, the immense heat and pressure on this planet are key factors contributing to the transformation of carbon into diamond. The process begins deep within the planet, where temperatures are high enough to melt the carbon. This molten carbon, under the planet's intense gravitational pressure, gradually crystallizes into diamond. It is a process similar to how diamonds form on Earth, but on a larger scale and at higher temperatures. On Earth, diamonds form about 150 kilometers below the surface, under high temperatures and pressures for billions of years. In contrast, in 55 Cancri e, this process is enhanced by the planet's extreme conditions, potentially leading to a surface layer largely of diamonds. This diamond formation is supported by observations of 55 Cancri e's density and the carbon-rich composition of the star. The incredibly high density suggests that it is not composed of light elements such as hydrogen and helium, like many gas giants, but of such as carbon, combined with the carbon-rich nature of its parent star. This leads scientists to conclude that 55 Cancri e could, in fact, be a diamond world. The presence of valuable materials, such as diamonds, on planets like 55 Cancri e offers a deep insight into the various processes of planet formation and the conditions that prevail in different parts of our universe. This revelation underscores the fact that planets can form under vast conditions that give rise to a wide variety of compositions and characteristics. When we observe a planet rich in diamonds, this tells us that the cosmic neighborhood is full of worlds that are not only very different from our own, but also from each other, highlighting the incredible diversity of planetary systems. This diversity is largely due to the materials available in the planet-forming regions around their host stars. In the case of 55 Cancri e, the high concentration of carbon relative to other elements suggests that its formation region was rich in carbon-based materials. This contrasts with Earth, where silicon and oxygen are more abundant, resulting in a rocky surface. The formation of a diamond planet indicates that the protoplanetary disk for which it formed had a unique chemical composition, emphasizing the role of stellar and molecular cloud environments in determining planetary composition. The process by which these materials are transformed under extreme conditions, such as the high pressure and temperature that leads to the formation of diamonds, provides valuable clues about the internal processes and heat dynamics of these distant worlds. This suggests that there are planets with internal mechanisms of heat and pressure very different from those found on Earth, which offers new avenues for research in geophysics and planetary chemistry, and to understand the formation of planets with surfaces rich in valuable materials also has implications for our knowledge of the life cycle of stars and planetary systems, hints at the evolutionary trajectories that planetary systems can take and the fate of planets over billions of years for. Example, a carbon-rich planet could evolve differently over time compared to a water-rich planet or a gas giant, which would affect its surface conditions, its atmosphere, and its potential to harbor diverse forms of music matter. The rings of J147b, an exoplanet located hundreds of light-years from Earth, represent one of the most spectacular phenomena discovered in the field of exoplanetary science. These rings are not only enormous, but incredibly extensive, far surpassing anything in our solar system. To put its scale into perspective, the rings of J1407b are so large that they dwarf the ring system of Saturn, the jewel of our solar system, by an astonishing margin. Let's imagine the rings of Saturn, which are already a marvel to behold from Earth, And then imagine a ring system in which the rings of Saturn would fit more than 200 times. That is the scale we're talking about with J1407b, the exoplanet. The rings span almost 90 million kilometers, about 56 million miles in diameter, about 200 times the size of Saturn's rings, offering a clear illustration of the incredible diversity of planetary systems in the universe. The discovery of the rings of J1407b has provided astronomers and scientists with a fascinating insight into the possibilities of planetary formation and the dynamics of ring systems. These rings are likely to contain particles of icy rock and possibly even moonlets or smaller bodies orbiting around J147b, similar to the shepherd moons found in the rings of Saturn. The enormous extent of the rings of J147b suggests that they could be the remnants of a massive collision or the early stages of the formation of a moon, shedding light on processes that could have occurred in the early solar system, but on a much larger scale, establishing parallels with our own solar system. Saturn's rings have shown us how moons can form within a planet's ring system. In the case of Saturn, the particles of ice and rock within its rings interact under the planet's gravitational influence, sometimes merging to form moonlets and, over time, potentially larger moons, given the size and mass of the rings of J1407b, which far exceed those of Saturn. It is plausible to suggest that, on this larger scale, similar processes of accretion and moonlet formation could be taking place. The theory postulates that, as particles within the rings collide and join, they gradually accumulate to form larger objects that, over time, could accumulate enough mass to clear their orbits within the ring, a critical step to becoming full-fledged moons. This process, although slow and complex, is a fascinating aspect of planetary science that provides insight on how moons and other small bodies in the solar system could have formed. The formation of moons within the rings of J1407b could have important implications for our understanding of planetary systems and ring dynamics. The observation and study of such a process would offer valuable data on the conditions necessary for the formation of the moon, the timescales involved, and how newly formed moons can affect the structure and stability of the rings. Music. Ol-25 BLG, 390 pounds, has been classified as an ice ball planet due to its extremely cold surface temperatures and its location in a distant orbit from its parent star, making it one of the coldest exoplanets discovered to date, located about 21,500 light-years from Earth in the constellation of Sagittarius. This remote world orbits its star at a considerable distance, much greater than Earth's distance from the Sun, which makes the heat reaching the planet minimal. The term ice ball aptly describes Ogle 20005 BLG, 390 pounds, as its surface temperature is estimated to be around minus 220 degrees Celsius, which makes it so cold that the water on its surface would be permanently frozen, creating an icy landscape across the planet. The categorization is based on the planet, its thermal characteristics, and its environment, unlike the ice giants of our solar system, such as Uranus and Neptune, which have significant atmospheres that contain gases such as hydrogen and helium. It is believed that an ice ball planet, such as Ogle 2005 BLG, 390 pounds, has a solid surface covered in ice. The extreme cold is attributed to its distant orbit, which prevents it from receiving enough solar energy to heat its surface above the freezing point of water. This classification provides an insight into the diversity of planetary environments that exist in our universe. Ice ball planets like Ogle 2005 BLG 390-pound challenge our understanding of habitability and the conditions necessary for life, while the harsh, icy conditions of such a planet would seem inhospitable to life as we know it. The study of these worlds helps scientists understand the outer limits of planetary climates and the potential of water in its various states in different celestial bodies. In planetary science, a planet's temperature plays a crucial role in determining its atmosphere composition. For a planet as cold as Ogle 2005 BLG 390 pounds, volatile compounds that are gases at warmer temperatures, such as water vapor, carbon dioxide, and methane, could freeze and deposit on the surface in the form of snow or ice. This process significantly reduces the atmosphere's thickness and density, as fewer gases remain in a vaporous state to form an extensive atmospheric layer. The lack of a substantial atmosphere on an ice planet like Ogle 2005 BLG 390 pounds also means that any heat from its star or internal heat generated by the planet itself would not be efficiently trapped, exacerbating the cold conditions. This contrasts with planets that have dense atmospheres, where greenhouse gases can trap heat and maintain a relatively warm environment even at significant distances from their stars. The temperature and potential atmospheric conditions on Ogle 2005 BLG 390 pounds offer information about the planet's ability to harbor life as we know it. The absence of a substantial atmosphere and the extreme cold greatly diminish the likelihood of liquid water existing on the surface, a key ingredient for life on Earth. However, these conditions also open up intriguing questions about the types of life that could exist in extreme environments, or what scientists call extremophiles, which expand the limits of our understanding of habitability in the universe. The study of distant and cold planets like Ogle 2005 BLG 390 Libby, located thousands of light years from Earth, involves the use of advanced astronomical techniques and technologies. Scientists rely on a combination of observational strategies and theoretical models to uncover the secrets of such remote worlds, despite the enormous distances and their faint visibility. Gravitational microlensing is one of the key methods used in the discovery and study of Ogle 2005 BLG 390 pounds. This phenomenon occurs when the gravity of a star or planet acts as a lens and bends and magnifies the light from a background star, the source, as it passes in front of it from our point of view. This effect can reveal the presence of planets around the foreground star, including details about their mass and distance from the host star. Gravitational microlensing is particularly powerful for detecting exoplanets that are too far away or too faint to be observed through more conventional methods, such as the transit method or direct imaging. It allows astronomers to detect planets that do not emit light themselves and are far from their host stars, making it ideal for discovering cold ice planets like Ogle 2005 BLG 390 pounds. The technique does not rely on the light of the host star or the planet itself, but on how the planet's gravity affects the light of a more distant star. This method has the unique advantage of being sensitive to low-mass planets and can detect them at a wide range of distances from their host stars. In addition to gravitational microlenses, scientists use computer models and simulations to predict and understand the conditions of such planets. By introducing the known physical characteristics of the planet, such as its mass, distance from its star, and orbital period into these models, scientists can make informed conjectures about the planet's atmosphere, surface conditions, and potential to harbor water or ice. These models help astronomers infer the planet's temperature, atmospheric composition, and potential for a solid surface. Telescopes equipped with sensitive instruments, both terrestrial and space-based, play a crucial role in tracking the discoveries made through microlenses, as they can provide additional data on the characteristics of stellar systems, helping refine measurements and confirm the presence of planets. Although direct observations of the planet's atmosphere or surface are difficult at such great distances, the combination of these techniques provides scientists with valuable information about the nature of these distant worlds. Music. The status of Kelt 9b as the hottest known exoplanet is a direct result of several extreme factors that combine to create its scorching conditions. Located about 670 light-years from Earth in the constellation Sagittarius, Kelt 9b orbits its host star, Kelt 9, which is one of the key factors contributing to its high temperature. This star is almost twice as hot as our Sun, making it one of the hottest stars known to host a planet. The proximity of Kelt 9b to its star is surprisingly close, with an orbital period of only about 15 Earth days. This very tight orbit places Kelt 9b in an intense stellar environment, receiving a colossal amount of radiation from its host star. The high temperature of the star and the planet's close orbit mean that Kelt 9b is subjected to thousands of times the radiation that the planets in our solar system receive from the Sun. This exposure heats the atmosphere of Kelt 9b to more than 4,300 degrees Celsius, about 7,800 degrees Fahrenheit, hotter than many stars and well above the melting points of most materials found on Earth. These extreme temperatures are responsible for truly exotic atmospheric chemistry and physics, including the possibility of vaporized metals and the total destruction of molecular hydrogen, which is abundant in the atmospheres of other gas giants. Another factor contributing to the high temperatures of Kelt 9b is the lack of a significant reflective atmosphere. Planets that can reflect some of their star's light back into space can moderate their temperature somewhat. However, the intense heat of Kelt 9b likely prevents the formation of reflective clouds or ice, allowing the planet to absorb the maximum amount of stellar radiation. The tidally locked nature of the planet, in which one side always faces the star while the other remains in perpetual darkness, could exacerbate temperature extremes. However, even with the potential distribution of heat by atmospheric winds, the daytime side of Kelt 9b remains infernally hot, showing the extreme conditions that exoplanets can present. For Kelt 9b, the hottest known exoplanet, future observations aim to delve deeper into its extraordinary atmosphere and the extreme conditions resulting from its proximity to its host star, Kelt 9. Astronomers are particularly interested in using the next generation of space and ground-based telescopes to further explore this intriguing world. One of the main objectives is to study the atmospheric composition of Kelt 9b in greater detail. This involves identifying the presence of exotic molecules and elements that may exist in vapor form due to the planet's high temperatures, such as vaporized metals and possibly even unknown or rare molecules in cooler planetary atmospheres. Another central point of future observations is the investigation atmospheric dynamics and weather patterns of Kelt 9b. Given the extreme temperature differences between the planet's day side and night side, scientists are very interested in understanding how heat is distributed throughout the planet. Scientists are very interested in understanding how heat is distributed throughout the planet, as this could reveal information about the potential for extreme weather phenomena never seen in our solar system. Advanced telescopes, such as the James Webb Space Telescope, JWST, and the Extremely Large Telescope, ELT, are expected to play a crucial role in these observations. The JWST, with its unprecedented sensitivity to infrared light, will be able to detect the thermal emission from Kelt 9b, providing detailed data on the planet's temperature distribution and atmospheric composition. The ELT, with its enormous mirror size, will offer unprecedented resolution, allowing astronomers to study the atmospheric chemistry of Kelt 9b with greater precision than ever before. In addition, future observations will seek to understand Kelt 9b's magnetic field and its interaction with the stellar wind from Kelt 9. This interaction is crucial to understanding the planet's atmospheric loss and how it affects the planet's long-term evolution and, its stability. The extreme seasonal changes in HD 80606b, a gas giant exoplanet located about 190 light-years away in the constellation Ursa Major, are mainly caused by its highly eccentric orbit around its host star, unlike the nearly circular orbits of the planets in our solar system. HD 80606b follows an elongated path that brings it extremely close to its star at periastron, the closest point in its orbit, and then moves it far away at apastron, the farthest point in its orbit. This unique orbital characteristic gives rise to dramatic variations in the planet's temperature and weather conditions throughout its orbit, which lasts about 111 days. As HD 80606b approaches its periastron, it experiences a rapid increase in temperature due to the intense solar radiation from its nearby star, which can cause the planet's atmosphere to heat up hundreds of degrees in just a few hours, a phenomenon unparalleled in our solar system. The sudden increase in temperature is believed to cause extreme weather phenomena, such as supersonic winds and storm systems that can span the entire planet. These conditions contrast with the much colder and calmer climate experienced when the planet is at apastron away from the star. The extent of these seasonal changes is further influenced by the planet's rotation and the angle of inclination of its orbit. If HD 80606b is tidally locked with one side always facing the star, the temperature contrast between its day side and night side would be even more pronounced. However, even if the planet rotates, the rapid heating and cooling as it moves along its eccentric orbit would still cause significant seasonal changes. Astronomers studied these extreme seasonal changes using various methods, such as transit observations, when the planet passes in front of its star from our perspective, and radial velocity measurements, which track the star's movement in response to the planet's gravitational pull. These observations help scientists understand the dynamics of the atmosphere of HD 80606b and the effects of its eccentric orbit on its climate. The extreme seasonal changes in HD 80606b, driven by its highly eccentric orbit, have important implications for the planet's potential habitability. The intense fluctuations in temperature and weather conditions, ranging from scorching heat to relatively cooler periods, create a difficult environment for the development and sustainability of life as we understand it. The rapid increase in temperature when the planet approaches its periastron can cause the atmosphere to heat up hundreds of degrees in just a few hours, leading to extreme conditions that make life difficult. The concept of habitability usually involves a stable environment in which liquid water can exist on the planet's surface, a condition believed to be necessary for life. However, the drastic temperature changes in HD 80606b would make it difficult for liquid water to maintain a stable presence during the planet's approach to its star. Any water on the surface would likely evaporate due to the extreme heat, while at the farthest points in its orbit, the remaining water could freeze. The planets orbiting the pulsar PSRB 1257+12 represent one of the most intriguing and unexpected discoveries in the field of astronomy, challenging our understanding of where and how planets can form. Pulsars are highly magnetized neutron stars. Highly magnetized rotating neutron stars that emit beams of electromagnetic radiation from their magnetic poles. As these neutron stars rotate, their beams of radiation sweep the Earth, creating a pulsating signal that can be detected by radio telescopes. The discovery of planets. Orbiting PSRB 1257+12, a pulsar at approximately 2,300 years of light from Earth in the constellation of Virgo, was revolutionary because it demonstrated, for the first time, that planets could exist in environments very different from the solar system. What makes these planets unique is not only their existence around a pulsar, but also the conditions in which they exist. Pulsars are remnants of massive stars that exploded as supernovas, leaving a core so dense that atoms are crushed into a sea of neutrons. The environment around a pulsar is extremely hostile, with intense radiation levels that would be inhospitable to life as we know it. The presence of planets in such an environment raises fascinating questions about their formation and their survival. Traditional theories of planetary formation, which involve the accretion of dust and gas in a protoplanetary disk around a young star, do not easily apply to the environment around a neutron star. It should have been cleared of such material by the star's supernova explosion. The planets orbiting PSRB 1257+12, discovered in the early 1990s, include several Earth-mass bodies, and their detection was a milestone in the field of exoplanetary science. His discovery was made through precise measurements of the timing of the pulsar's pulses as the planets orbiting a pulsar cause it to wobble slightly due to its gravitational pull, causing tiny but measurable variations in the timing of its pulses. This detection method is unique to pulsar planets and showcases the diversity of techniques astronomers use to discover exoplanets. Another notable aspect of these pulsar planets is their possible formation mechanism. One theory suggests that these planets could have formed from remnants of a supernova that created the pulsar, representing a second generation of planetary formation. Alternatively, they could have been pre-existing bodies captured by the pulsar's gravity or remnants of a stellar system that survived the supernova explosion in some way. The discovery of planets orbiting the pulsar PSRB 1257 plus 12 opened a new avenue for exoplanet research, demonstrating that planets could form or survive in extreme environments and conditions previously thought to be uninhabitable. The conditions on the planets orbiting the pulsar PSRB 1257 plus 12 are very different from those of the planets in our solar system, presenting an environment that is almost incomparable. The planets in our solar system orbit a stable main sequence star, the Sun, which provides a relatively constant source of light and heat, crucial for maintaining conditions that support life on Earth and influence the climate and atmospheric dynamics of other planets. In contrast, the planets orbiting PSRB 1257 plus 12 orbit a pulsar, an extremely dense remnant of a supernova explosion that emits intense electromagnetic radiation and has powerful magnetic fields. The radiation environment around a pulsar is incredibly hostile compared to the sunlight bathing our solar system. The radiation from pulsars can strip atmospheres, irradiate surfaces, and potentially sterilize planets, making them inhospitable to life as we know it in our solar system. Planets like Earth have magnetic fields that protect them from solar wind and cosmic rays, preserving their atmospheres and harboring life. The planets around PSRB 1257 plus 12, however, are exposed to radiation from the pulsar with little or no protection, suggesting that any atmosphere they might have could be very thin or non-existent. The formation mechanism of planets around a pulsar is probably very different from that of our solar system. While the planets in our solar system formed from the protoplanetary disk of gas and dust surrounding the young sun, the planets surrounding PSRB 1257 plus 12 may have formed from the remnants of the supernova that gave rise to the pulsar, suggesting a second generation of planetary formation that could involve different materials and processes than those that created the planets in our solar system. Temperature conditions also present a stark contrast as the planets in our solar system experience temperatures that can support liquid water on Earth and ice on the outer planets, while the planets orbiting PSRB 1257 plus 12 are likely subject to extreme temperature variations, depending on their distance from the pulsar and the intensity of its emissions. These conditions are far removed from the relatively stable environments we find in our solar system, where the sun's energy allows for a variety of climates and music atmospheric conditions. Corot 2b, an exoplanet discovered by the convection, rotation, and planetary transits Corot space mission, presents a fascinating case of a planet impacting its host star in a way observable from Earth. It orbits its host star, Corot 2a, every 17 days. Corot 2b is a hot Jupiter, a type of gas giant that orbits very close to its star. This proximity causes several significant effects on the star itself, highlighting the dynamic interactions that can occur between a star and its planets. One of the most striking impacts of Corot 2b on its host star is the phenomenon known as star-planet interaction. The intense gravitational pull of Corot 2b can induce activity in the outer layers of the star, which could lead to increased magnetic activity, including star spots and flares. These effects are somewhat analogous to the way the moon influences Earth's tides, but on a much larger scale, with magnetic fields and stellar plasma. The proximity of Corot 2b to its host star subjects it to tremendous stellar radiation that heats the planet's atmosphere to extreme temperatures. This heating can cause the planet's atmosphere to expand and, in some cases, escape into space. As the atmosphere bleeds away, it forms a cloud of material around the planet that can interact with the star. This interaction can cause a transfer of angular momentum from the planet to the star, affecting the star's rotation rate and its magnetic field. Another intriguing aspect of the Corot 2 system is the possibility that the planet induces chemical changes in the outer layer of the host star. The material lost from the planet's atmosphere could fall into the star, altering its chemical composition and spectral signature. This process, known as accretion, can provide astronomers with clues about the composition of the planet's atmosphere based on the changes observed in the star's spectrum. Astronomers study these interactions using various methods, including spectroscopy, which analyzes light from stars to identify chemical compositions and changes in brightness and magnetic activity. Observations of the Corot-2 system contribute to our understanding of how planets can affect their stars, offering information on the evolution of planetary systems and the complex dynamics governing their behavior. The interaction between Corot-2b and its host star, Corot-2a, sheds light on the complex and dynamic relationships that can exist between stars and their planets, expanding our understanding of the cosmic dance that unfolds throughout the universe. These interactions reveal that planets, especially those in close orbits, such as hot Jupiters, can have a profound impact on their stars, influencing their magnetic activity, their rotation rates, and even their chemical composition. This dynamic contrasts with the previously held view that stars exclusively dictated the conditions of planets orbiting them, with no reciprocal effect. The phenomenon of star-planet interaction, exemplified by the Corot-2 system, suggests that planets can induce magnetic disturbances in their host stars, which leads to increased stellar activity, like flares and spots. This is particularly significant because it implies that the presence and properties of planets can directly affect the stellar environment, altering the conditions in which these celestial bodies exist and evolve. In the case of Corot-2b, the proximity to its host star and the resulting gravitational forces show how a planet's influence can extend beyond its own atmosphere, affecting the star's orbits. These interactions highlight the potential for atmospheric loss from planets subjected to intense stellar radiation. The process of stripping a planet's atmosphere and possibly feeding the star introduces a bidirectional exchange of material between stars and planets, blurring the lines of their relationships. This exchange of material can cause changes in the chemical composition of the outer layers of a star, which provides astronomers with indirect methods to study the atmospheres of exoplanets by observing their music. The star's the phenomenon of ruby rain on HAT P7b, an exoplanet located about 1040 light-years from Earth, is a captivating aspect of the atmospheric dynamics driven by the extreme conditions present in this gas giant. HAT P7b is a type of exoplanet known as a hot Jupiter due to its size similar to Jupiter, but much closer to its host star, resulting in higher temperatures. The unique weather pattern, which includes the precipitation of materials such as rubies and sapphires, is attributed to the presence of aluminum oxide in the planet's atmosphere. In the conditions of Earth, aluminum oxide crystallizes to form corundum, the base mineral of gems, such as rubies and sapphires, depending on the type of trace impurities it contains. The high temperatures on HAT P7b's day side allow the formation of aluminum oxide vapor in the atmosphere. The planet's close orbit subjects it to intense stellar radiation around its host star, which heats the atmosphere to temperatures at which metals vaporize and complex chemical reactions can occur. As the vapor is transported to the cooler night side of the planet by strong winds, the drop in temperature allows the aluminum oxide to condense and form clouds. Further cooling can cause the precipitation of corundum crystals that fall as rain in the planet's atmosphere, depending on specific local conditions, such as the presence of trace elements such as chromium or iron. These corundum crystals could theoretically resemble rubies and sapphires, hence the poetic description of them being raining gems in HAT P7b. This extraordinary meteorological phenomenon is part of what makes the study of exoplanets so fascinating, as it offers a vision of the wide range of environmental conditions that can exist beyond our solar system. Dynamics of the atmosphere of HAT P7b, including the formation of gemstone rain, is studied through observations of the planet's brightness variations and spectral analyses that reveal information about its atmospheric composition and temperature distribution. These studies provide crucial information about the atmospheric chemistry and climatic processes of hot Jupiters, expanding our understanding of planetary science. Music. Music, the extraordinary phenomenon of iron rain on WASP 76b, a planet located about 640 light-years away in the constellation Pisces, is a direct consequence of the extreme temperature differences and the unique atmospheric dynamics of this ultra-hot Jupiter. WASP 76b orbits very close to its host star, completing an orbit in about 18 Earth days, which subjects one side, the day side, to intense stellar radiation. Its proximity to its star causes daytime temperatures to soar above 2,400 degrees Celsius, approximately 4,350 degrees Fahrenheit, hot enough to vaporize even iron. The mechanism behind the iron rain involves the vaporized iron being transported from the day side to the cooler night side of the planet as the ion-laden atmospheric currents move to the night side, where temperatures are significantly lower. The vaporized iron cools and condenses into droplets that form clouds that precipitate as iron rain. This marked temperature contrast between the day side and night side of the planet, combined with the efficiency of atmospheric heat distribution, creates the conditions necessary for this metallic precipitation. Observations and studies of WASP 76b, particularly through spectroscopy, have provided evidence of this phenomenon. Spectroscopy allows astronomers to detect the chemical signatures of elements in the planet's atmosphere by analyzing the light filtering through it. The presence of ion vapor on the day side, but not on the night side, suggests that the ion condenses and probably rains before it can circulate back to the day side. Music TOI 700D, an exoplanet discovered by NASA's Transit Exoplanet Exploration Satellite, TESS, has captured the attention of scientists and space enthusiasts alike due to its potential habitability, located about 100 light-years away in the constellation Dorado. TOI 700D is the outermost planet in its stellar system, orbiting a small, cold M-type dwarf star. What makes TOI 700D particularly intriguing as a candidate for habitability are several key characteristics that set it apart from other exoplanets. TOI 700D is located in the habitable zone of its star, the region around a star where conditions could be right for liquid water to exist on a planet's surface, a crucial ingredient for life as we know it. The planet's orbit places it at a distance where it receives about the same amount of stellar energy from its star as Earth from the Sun. This balance suggests that temperatures on TOI 700D could allow for liquid water, provided it has a suitable atmosphere. TOI 700D is approximately the size of Earth, with estimates suggesting it has a radius about 12 times that of Earth. This size indicates that the planet could have a rocky composition similar to Earth, Mars, and Venus. Planets of this size are more likely to maintain a stable atmosphere, which is another critical component for potential habitability. An atmosphere could not only provide the gases necessary for life, but also regulate temperature by trapping heat through the greenhouse effect. The orbit of TOI 700D is also perfectly aligned with its star, which means that one side of the planet perpetually faces the star, while the other side remains in constant night. While this could lead to extreme temperature variations between the day side and night side, the presence of an atmosphere could help distribute heat more evenly around the planet, potentially stabilizing the climate enough for liquid water and, by extension, life. The host star, TOI 700, is a quiet M dwarf that exhibits fewer flares than other stars of its type. Stellar flares can strip a planet of its atmosphere and bombard its surface with harmful radiation, which is detrimental to habitability. The relatively quiet nature of TOI 700 enhances the habitability prospects of TOI 700D by minimizing these. Music risks LHS 33844b, an exoplanet orbiting a red dwarf star approximately 486 light-years away in the constellation Indus, exhibits extreme temperature differences between its day side and night side due to a combination of its proximity to its host star and its likely lack of a significant atmosphere. This terrestrial planet completes an orbit in just 11 hours, placing it much closer to its star than Earth is to the Sun. Such a close orbit causes the planet to receive a large amount of stellar radiation on its day side, resulting in extremely high temperatures. The most important factor contributing to the temperature contrast between the day side and night side of LHS 3844b is its tidally locked nature. This means that the same side of the planet always faces the star, receiving constant sunlight, while the opposite side remains in perpetual darkness without an atmosphere to redistribute heat around the planet. The temperature on the day side can reach very high, while the night side remains much colder due to the lack of direct stellar heating. Observations and studies, including those made with NASA's Spitzer Space Telescope, have provided evidence suggesting that LHS 3844b has little or no atmosphere. An atmosphere plays a crucial role in a planet's climate by circulating heat, as on Earth. For example, the atmosphere helps moderate temperatures across the planet by distributing heat from the equator to the poles. The apparent absence of an atmosphere on LHS 3844b means that heat from its star is not efficiently distributed throughout the planet. As a result, the temperature on the side of LHS 3844b that faces its star can reach approximately 800 degrees Celsius, 1,472 degrees Fahrenheit, while the night side can be drastically colder. With a significant temperature drop, Gle 1214b is considered a super-Earth because it is an exoplanet larger than Earth, but smaller than the ice giants Uranus and Neptune, with a mass and radius that suggest a different composition than that of the rocky planets of our solar system. Specifically, Gle 1214b has about 65 times the mass of the Earth, and a radius approximately 27 times greater than that of the Earth, which places it in the category of super-Earths due to its size and mass. This classification is important because it indicates that Gle 12144 could have a variety of characteristics, including a dense atmosphere, the possibility of liquid water, or even a world covered by an ocean, depending on its composition and the conditions present in its atmosphere. The term super-Earth does not necessarily imply that the planet is habitable or similar to Earth in terms of climate and conditions, but refers to the size of the planet, which is between that of Earth and Neptune, and suggests a diversity in the types of planets that exist beyond our solar system. Super-Earths like Gle 1214b are of special interest to astronomers because they represent a class of planets not found in our solar system and offer unique opportunities to study planetary formation, evolution, and the potential for life in conditions different from those of Earth. Gle 1214b orbits a red dwarf star located about 48 light-years away in the constellation of Fucus. Its relatively short orbital period of about 38 hours means that it is very close to its host star, which influences the temperature and atmospheric conditions of the planet. Observations suggest that Gle 1214b has a dense atmosphere that could be composed of water vapor or other heavy molecules, leading to speculation about the conditions of its surface and the possibility of an exotic form of water under high pressure and temperature known as an aquatic world. The study of Gle 1214b and other super-Earths is crucial to advance our understanding of planetary diversity across the universe. By analyzing the atmospheres of these planets through techniques such as transit spectroscopy, scientists can obtain information about their chemical composition, climate patterns, and, potentially, their ability to harbor life. This research not only expands our knowledge of exoplanets, but also helps refine models of planetary systems and the formation of planets in variable conditions. Music. Proxima Centauri b, which orbits around the star closest to the Sun, Proxima Centauri, approximately 42 light-years away in the constellation of Centaurus, emerges as a prime candidate in the search for extraterrestrial life due to several compelling characteristics. First, its location within the habitable zone of its star is a critical factor. This zone, often referred to as the Goldilocks zone, is the range of distances from a star where conditions could be right for liquid water to exist on the surface of a planet, an essential ingredient for life as we understand it. Proxima Centauri orbits within this zone, suggesting that it has the potential to maintain surface temperatures that could support liquid water, assuming it has a suitable atmosphere. Another factor that reinforces the case of Proxima Centauri b as a candidate to harbor life is its size, similar to that of Earth. Estimates of the planet's mass indicate that it is at least 117 times greater than that of Earth, which points to a rocky rather than gaseous composition. This similarity in size and implicit composition with Earth increases the probability that Proxima Centauri b may have environmental conditions similar to those of Earth, which further reinforces the potential for habitability. The proximity of Proxima Centauri b to Earth offers a unique advantage for astronomical observation and study, since it is the closest known exoplanet and is a priority target for future missions and telescopes designed to study exoplanetary atmospheres. The conditions of the surface and possible biosignatures. Advanced technologies and advanced telescopes, such as the James Webb Space Telescope, could provide the ability to analyze the chemical composition of the planet's atmosphere, look for signs of water, and detect molecules that could indicate biological processes. However, there are challenges associated with the potential habitability of Proxima Centauri b. Proxima Centauri is a red dwarf star known for its stellar flares and high levels of stellar activity, which could pose a threat to the atmosphere and surface conditions of Proxima Centauri b. For life to exist as we know it, the planet would need a robust magnetic field to protect it from the star's radiation and preserve its atmosphere. The status of Proxima Centauri b as a leading candidate in the search for extraterrestrial life is based on its orbit within the habitable zone of its star, its size similar to that of Earth, and its position as the exoplanet closest to our solar system. These factors, combined with the potential for future direct observations, make Proxima Centauri b a point of interest for scientists seeking to discover signs of life beyond Earth. Kepler-22b, an exoplanet discovered by NASA's Kepler Space Telescope, has aroused considerable interest in the scientific community due to several characteristics that suggest it could be capable of harboring life. Located about 620 light-years away in the constellation of Cygnus, this planet orbits within the habitable zone of its star, Kepler-22, a region where conditions may allow the existence of liquid water, a fundamental requirement for life as we know it. One of the main reasons for the interest in Kepler-22b is its position in the habitable zone. This location means that the planet receives an amount of stellar radiation similar to that received by Earth from the Sun, which could allow a climate that supports water in liquid form on its surface. The importance of liquid water cannot be underestimated, as it is considered a critical ingredient for the biochemical processes known to sustain life. In addition, Kepler-22b is approximately 24 times the radius of Earth, which classifies it as a super-Earth, while its mass and composition remain uncertain due to the limitations of current observation techniques. There is the possibility that Kepler-22b has a rocky surface or a surface covered by a global ocean, a scenario that could be conducive to life. The concept of a planet covered in liquid water without land breaking the surface opens up intriguing possibilities for aquatic life forms. The star Kepler-22 also plays a role in the potential habitability of Kepler-22b. It is a star of a type similar to the Sun, although slightly smaller and colder. The stability and characteristics of G-type stars are believed to be conducive to the development of life, as they provide a constant and lasting source of energy. The relatively calm stellar environment in comparison with more volatile types of stars, such as red dwarfs, known for their powerful eruptions, suggests that Kepler-22b could maintain a stable atmosphere. However, the ability of Kepler-22b to harbor life does not depend only on its location within the habitable zone and the nature of its host star, but also on its atmospheric composition, which remains unknown. An atmosphere dense enough to retain heat through a greenhouse effect, but not so dense as to cause uncontrolled warming or be hostile to life, would be ideal. Future observations with more advanced telescopes, such as the James Webb Space Telescope, could provide information about the atmosphere of Kepler-22b, including the presence of gases that could indicate biological activity. The planet WASP-17b, discovered in 2009, challenges conventional planetary behavior with its unique and intriguing characteristics, which has earned it the nickname of the Upside-Down Giant. This gas giant is located about 1,000 light-years away in the constellation of Scorpio and is one of the exoplanets discovered with a radius almost twice that of Jupiter, but it only has half of its mass, which results in an exceptionally low density that resembles it to a celestial ball in space. However, what most clearly distinguishes WASP-17b is its retrograde orbit, which moves in the opposite direction to the rotation of its host star, a rare phenomenon among the planets discovered outside our solar system. The retrograde movement of WASP-17b challenges the traditional models of planetary formation and migration. According to these models, planets are formed from a circumstellar disk of gas and dust, and their orbits are initially aligned with the rotation of the parent star. The retrograde orbit of WASP-17b suggests a turbulent past that implies gravitational interactions with other planetary bodies or a nearby star that could have drastically altered its original trajectory. This could include scenarios such as close encounters with other planets that cause gravitational slingshots, or a more gradual process known as Chi cycles, which can exchange the orbital inclination of a planet for eccentricity over time, which could reverse its orbit in relation to the rotation of the stars. Another fascinating aspect of WASP-17b involves the properties of its atmosphere. Observations indicate the presence of water vapor and possibly even carbon monoxide, but the extended atmosphere and its low density raise questions about its composition and the dynamics of its weather patterns. The intense radiation it receives, due to its proximity to its host star, could cause extreme atmospheric phenomena, unlike anything observed in our solar system. Music, a system located outside our solar system, about 560 light-years away in the Draco constellation. This planet orbits its host star, Kepler-10, at a remarkably close distance, completing a full orbit in just under 20 hours. This proximity to its star subjects Kepler-10b to extreme temperatures, earning it the nickname the roasted rocky world. The intense radiation from its host star heats the surface of Kepler-10b to more than 1,300 degrees Celsius, a temperature that can melt iron and rock, creating a landscape covered in lava. This extreme heat makes Kepler-10b an unlikely candidate to harbor life as we know it, but provides a unique laboratory to study the compositions and atmospheres of rocky exoplanets, as well as the conditions in which they form and evolve. The composition of Kepler-10b is mainly siliceous rock with a mass approximately 33 times greater than that of Earth, and has a radius 147 times greater than that of our planet. These characteristics confirm its status as a terrestrial or rocky planet, similar in composition to Earth, Venus, Mars, and Mercury in our solar system. However, unlike the rocky planets that orbit our Sun, Kepler-10b's close orbit and resulting high surface temperatures highlight the diversity of planetary environments that exist in the galaxy. The discovery of Kepler-10b was significant not only for confirming the existence of rocky exoplanets, but also for demonstrating the capabilities of the Kepler telescope and the transit method to detect exoplanets by monitoring the slight dimming of a star's light when a planet passes in front of it. Astronomers can collect critical information about the planet's size, density, and orbit. In the case of Kepler-10b, these observations have provided valuable data on the properties of rocky planets, including their densities, which in turn offer clues about their composition and structure. The extreme proximity of Kepler-10b to its host star also raises questions about its formation and history. The planet likely formed further out in its solar system and migrated inward over time, a process that could have involved interactions with other planets or with the protoplanetary disk from which it originated. Understanding these dynamic processes is crucial to reconstructing the history of planetary systems, including our own. Music, our own Gliese 436b, an exoplanet located about 3033 years light away in the Leo constellation, presents a paradoxical phenomenon that has intrigued astronomers since its discovery, known as the burning ice planet. This world defies traditional expectations about planetary conditions and composition. Despite orbiting very close to its host star, Gliese 436, with a scorchingly short orbital period of just over 2 days, the planet is covered in what is known as hot ice, a state of water that exists under extreme pressure and high temperatures. The surface temperature of Gle 436b exceeds 400 degrees Celsius, 750 degrees Fahrenheit, conditions in which water would normally be expected to exist as steam. However, the immense gravitational pressure on Gle 436b is so great that it forces the water into an exotic form of ice known as Ice X. This form of ice does not melt into liquid water at higher temperatures, but remains solid due to the pressure exerted on it, creating a scenario in which ice can exist in a near-stellar environment. This peculiar state of matter in Gle 436b is the result of its unique atmospheric and physical characteristics. The planet's atmosphere is rich in hydrogen and helium, with traces of water vapor, suggesting that water is present on the planet. However, due to the extreme conditions, this water does not exist in familiar states, but the high temperatures and pressures transform it into hot ice and a supercritical fluid, a state of matter that exhibits properties of both liquids and gases. The discovery of Gle 436b has significantly expanded our understanding of the diversity of exoplanets and the variety of conditions in which they can exist. This challenges preconceived ideas about the behavior of water and the conditions necessary for different states of matter to form. The existence of hot ice on Gle 436b suggests that there may be many more planets with equally exotic conditions that defy easy categorization and expand the possibilities of the conditions that planets in the universe can present. Music. HD 209458b, also known as Osiris, stands out in the pantheon of exoplanets for its dramatic and visible evaporation process, located about 150 light-years away. Music. HD 209458b, also known as Osiris, stands out in the pantheon of exoplanets for its dramatic and visible evaporation process. Located about 150 light-years away in the Pegasus constellation, this gas giant orbits its host star at a mere eighth of the distance that separates Earth from the Sun, resulting in extremely high surface temperatures exceeding 1,000 degrees Celsius, 1832 degrees Fahrenheit. This proximity to its star subjects HD 209458b to intense stellar radiation that causes its atmosphere to heat up and expand to the point of beginning to escape into space. The atmospheric escape phenomenon in HD 209458b was one of the first of its kind to be directly observed with the Hubble Space Telescope. Astronomers detected hydrogen, carbon, and oxygen ejected from the planet at speeds of thousands of kilometers per hour, creating a vast tail of material trailing behind the planet, much like a comet. This escape process is so significant that it is estimated that the planet may lose between 100 million and 500 million kilograms of mass per second. The evaporation of HD 209458b provides crucial information about the interactions between exoplanets and their host stars, especially in cases where planets are in close orbits. The intense radiation that drives atmospheric leakage on Osiris is also responsible for ionizing the escaping gases, which interact with starlight to produce the observable signals that led to the detection of this music phenomenon. Kepler-16b, an exoplanet located about 200 light-years away in the Sagittarius constellation, offers a vision of a world that seems straight out of science fiction, known as the land of the two suns. This planet is distinguished by its orbit around a binary star system, making it the first confirmed circumbinary planet, a planet that orbits two stars instead of one. This unique celestial configuration causes Kepler-16b to experience a double sunset and sunrise, reminiscent of iconic scenes from the Star Wars saga. The discovery of Kepler-16b was made possible by NASA's Kepler Space Telescope, which detected the planet using the transit method. This method involves observing the slight dimming of starlight when a planet passes in front of its host stars from the telescope's perspective. The transits of Kepler-16 revealed not only its existence, but also its remarkable orbit around the two members of a pair of stars that orbit very close to each other. One is slightly smaller than the Sun, and the other is much smaller, cooler, and redder. Kepler-16b is approximately the size of Saturn, with a mass and radius that suggest a gaseous composition, possibly with a rocky core. Its orbit around the binary stars lasts about 229 days, a distance that places it outside the habitable zone of its star system, suggesting that temperatures on Kepler-16b are likely too cold for liquid water to exist on its surface. Despite this, the planet's discovery has important implications for our understanding of the formation and dynamics of planetary systems around binary stars. The existence of Kepler-16b challenges the previous hypotheses about planetary formation, indicating that planets can form and maintain stable orbits even in the complex gravitational fields generated by two stars. This has expanded the search for exoplanets by astronomers to include binary and multiple star systems, common in our galaxy. In addition, the study of Kepler-16b and similar circumlunar planets helps scientists to refine the models of planetary formation and migration, offering information about the diversity of worlds that exist in the universe. Music GJ3470b, an exoplanet located about 100 light-years away in the constellation of Cancri, has caught the attention of the scientific community due to its significant atmospheric leakage. This Neptune-sized world orbits a red dwarf star, GJ3470, and is classified as a warm Neptune due to its size and the higher temperatures that it experiences compared to Neptune in our solar system. The phenomenon of its atmospheric leakage presents a unique opportunity for astronomers to study the processes of atmospheric loss in exoplanets, which can provide information about planetary evolution and the factors that influence habitability. The atmosphere of GJ3470b is escaping into space at an astonishing rate, a process that has been directly observed by astronomers using the Hubble Space Telescope and other observatories. The planet's proximity to its host star exposes it to intense ultraviolet, UV, and X-ray radiation, which heats the upper layers of its atmosphere to the point where hydrogen and other gases can reach escape velocity and break free from the gravitational pull of GJ3470b, where estimates suggest it could be losing up to 100 times more mass per year than a similar exoplanet. GJ436b, another warm Neptune known for its evaporating atmosphere. The rapid loss of atmosphere in GJ3470b raises questions about the future of the planet and what it could tell us about the life cycles of similar exoplanets over time. The continuous loss of atmospheric gases could significantly alter the composition of the planet, potentially transforming it from a gas-dominated world to a more rocky or Earth-like planet, although probably inhospitable due to its close orbit around an active red dwarf star. This transformation process, although it will take billions of years, offers a vision of the dynamic nature of planetary systems and the various final states that planets can reach. Music K218b, an exoplanet that orbits within the habitable zone of its star K218, located about 124 light-years away in the constellation of Leo, has aroused the interest of astronomers and astrobiologists alike. This planet is classified as a super-Earth due to its size and mass, which are several times greater than those of Earth, making it larger than typical rocky planets, but smaller than gas giants like Neptune or Jupiter. What distinguishes K2-18b and fuels discussions about its potential to harbor life is the detection of water vapor in its atmosphere, a finding that marks a significant milestone in the search for habitable worlds beyond our solar system. The presence of water vapor in the atmosphere of K2-18b was confirmed through observations made by the Hubble Space Telescope using a technique known as transit spectroscopy. As the planet passes in front of its host star from our perspective, light filters through its atmosphere, allowing scientists to analyze the light and identify the chemical signatures of various molecules, including water vapor. This method provides valuable information about the composition of exoplanet atmospheres and the conditions present on these distant worlds. The orbit of K2-18b is within the habitable zone of its star, a region where temperatures could allow for the existence of liquid water on a planet's surface, provided it has a suitable atmosphere. The discovery of water vapor in the atmosphere of K2-18b suggests that, under the right conditions, this planet could have liquid water, a crucial ingredient for life as we know it. However, it is important to note that the existence of water vapor in the atmosphere does not guarantee the presence of liquid water on the surface, nor does it directly indicate a planet is habitable. Atmospheric pressure, temperature, and other environmental conditions play an important role in determining whether water can exist in liquid form. The star K2-18 is a red dwarf smaller and cooler than our Sun, and red dwarfs are known for their stellar activity, which can affect the habitability of the planets that orbit them. Despite this, the specific conditions of K2-18b's orbit and atmosphere make it one of the most intriguing targets for further study in the search for habitable exoplanets. Future observations with more advanced telescopes, such as the James Webb Space Telescope, will seek to provide a more detailed understanding of the atmospheric sphere of K2-18b, including the possibility of the existence of other gases, such as nitrogen and oxygen, that may support a habitable environment. Music. WASP-121b, an exoplanet discovered orbiting a star located about 900 light-years away in the constellation of Puppis, has intrigued astronomers for its unique atmospheric characteristics. This planet is classified as an ultra-hot Jupiter, a gas giant more massive than Jupiter, but orbiting much closer to its star, resulting in extremely high temperatures. One of the most striking features of WASP-121b is the presence of a stratosphere, a layer in its atmosphere where temperature increases with altitude, similar to Earth's. This discovery marks a significant step forward in our understanding of exoplanet atmospheric dynamics. The existence of a stratosphere in WASP-121b was confirmed through observations by the Hubble Space Telescope. These observations revealed that water molecules in the planet's atmosphere absorb radiation from a star, causing the temperature in the upper atmosphere to increase. This process indicates the presence of a stratosphere, where temperature inversion can lead to temperatures exceeding 2,500 degrees Celsius, approximately 4,532 degrees Fahrenheit, in the upper layers. These high temperatures make WASP-121 be one of the hottest exoplanets studied so far. The ultra-hot conditions on WASP-121b also give rise to exotic atmospheric chemistry, including the dissociation of water molecules and the possible presence of metallic gases. The intense heat, due to the proximity of its star, causes part of the planet's atmosphere to escape into space, creating a tail similar to that of a comet. These extreme conditions provide a unique laboratory to study the chemical and physical processes in the atmospheres of the hottest exoplanets. The discovery of a stratosphere in WASP-121b is significant because it helps scientists understand how energy is absorbed and redistributed in hot Jupiter's atmospheres. This understanding is crucial for developing accurate models of atmospheric circulation and temperature distribution on exoplanets. As we finish our journey to some of the scariest planets in our universe, we are left with a deep understanding of the immensity and complexity of the cosmos. These distant worlds, with their extreme temperatures, volatile atmospheres, and alien landscapes, challenge our understanding of the universe and our place within it. Thanks for watching.